Welcome to the deep dive. We're the show that tries to cut through all that noise, the sheer amount of information hitting you every day.
Yeah, it's a lot. And figuring out what actually matters, that's tough.
Exactly. So, a mission here is simple. We do the digging, we find the core stuff, the surprising bits, maybe even make it a bit fun, and give you that shortcut to being genuinely well-informed.
You just bring your curiosity. We'll handle the rest. We've gone through, well, quite a stack of material for you on today's topic. Research, notes, history, all curated.
And today, we are diving deep into something that, might sound a bit heavy at first. Fourier transforms.
Right, the name itself sounds like serious math.
It does. But stick with us, because this isn't really about, complex equations written on a blackboard. It's about uncovering the basic recipe, the sort of hidden code behind almost every signal in our world.
Yeah, like the music you're streaming right now, the pictures on your screen, even how engineers figure out how to make buildings stand up during earthquakes. It's everywhere.
So, like you said, we've pulled together some fascinating sources, research papers, a study guide, FAQs, even some cool historical notes about where these ideas came from.
Our goal today, go past the math, find the intuition. What is this thing, really? Where did it come from? And why does it matter so much to, well, everything?
Let's jump in.
Okay.
Maybe the best place to start is with an analogy, something to make it click.
That's good.
Imagine you've got a smoothie. Delicious, maybe complicated, lots of fruits blended together.
Okay, I'm with you. A smoothie.
What does the Fourier transform do? It takes that smoothie and it figures out the exact recipe. How much strawberry, how much banana, how much spinach, whatever's in there.
That's a great analogy. So the smoothie is like any signal or pattern that changes over time. Could be sound waves, could be stock prices, could be light waves from a star.
Anything that fluctuates.
Right. And the Fourier transform process is like running that smoothie through a series of really specialized filters. Each filter is designed to measure one specific cycle or repeating pattern within that signal.
Right. And the output, the recipe you get.
That's the key part. It's the cycle recipe. It tells you for every possible cycle it finds. What's its amplitude? How strong is that cycle?
Okay, its intensity.
Exactly.
Yeah.
Then what's its frequency? How fast does it cycle or spin?
Right.
And finally, its phase angle. What's its starting position? Like where was it in its cycle right at the beginning at time zero?
Amplitude, frequency, phase, the recipe.
And here's why that recipe is so useful. It's often way easier to understand or analyze or even change the signal when you have this list of ingredients rather than just the mixed up smoothie. You can see the core components clearly.
That makes sense. Breaking it down helps. But what are these cycles exactly? You mentioned spinning. Why circles? I usually think of waves, like going up and down.
That's a really important distinction, actually.
Right.
We often visualize signals as 1D waves, like an EKG line moving up and down. That's a sinusoid.
Right.
But the Fourier transform, fundamentally, it breaks signals down into 2D circular paths. Think of something literally spinning around a center point.
Like the hands of a clock, but maybe smoother and at different speeds.
Precisely. And the math behind this often uses something called Euler's formula. It's just a neat way to represent these spinning motions using complex numbers, specifically complex exponentials. It sounds complicated, but it actually makes the math work out quite elegantly.
So it's all about circles spinning at different speeds, different sizes.
Different sizes, that's the amplitude, the radius.
Yeah.
Different speeds, that's the frequency. And different starting points, that's the phase angle. Those three things define each circular component.
Okay, conceptually, I'm sort of getting it. But how do a bunch of circles spinning add up to something really simple, like a single click or a flash, just one tiny spike in time?
This is where it gets kind of mind-bending, but really cool. To create what's called a time spike or a delta function, mathematically something that exists for just one instant.
Yeah.
You actually need an infinite number of these circular paths all added together.
Infinite. How does that work?
The trick is in the timing, the phase. At that one specific instant you want the spike to occur, all infinite cycles have to line up perfectly at their maximum point. They all constructively interfere right then.
Okay, so they all peak at the exact same moment.
Exactly. But then, for every other moment in time, before and after that spike,
They have to cancel out.
perfectly. Their combined sum has to be zero everywhere else. Imagine, like, 1,000,000 tiny spinning vectors. At one moment, they all point the same way, creating a huge combined vector. At all other moments, they're pointing in such precisely calculated different directions that they all cancel each other out completely.
Wow.
And those phase shifts we mentioned, the starting angles, they're crucial. By adjusting the starting phase of each cycle, You can control when that perfect alignment happens. You can move the spike around in time.
Like setting runners off at staggered times so they all cross the finish line simultaneously.
Exactly like that.
Yeah.
It's an incredible idea that even the simplest event, like a single click, is actually made of this infinitely complex, perfectly synchronized orchestra of cycles. It really shows how deeply connected time and frequency are.
That is pretty amazing. Okay, so this isn't just theoretical math. You mentioned earthquakes, music. Where else does this recipe finding actually show up? Where is it making a difference in the real world?
Oh, it's absolutely everywhere, especially in engineering and signal processing. Take those earthquakes. Engineers analyze the ground vibrations using Fourier transforms to find the dominant frequencies.
The main shake patterns.
Right. Then they can design buildings or bridges to not resonate strongly at those frequencies, making them much safer.
Clever.
In audio, it's fundamental. Noise cancellation headphones. They analyze the incoming noise frequencies and generate anti-noise at the same frequencies but opposite phase to cancel them out.
Ah, using that phase idea again.
Yep. Music apps that identify a song. They're looking at the unique frequency recipe of that song. Even just basic EQs on your stereo, boosting the bass or treble. That's manipulating frequency components identified by Fourier analysis. And tuning a radio. You're isolating one specific frequency band.
So pretty much anything involving sound or vibration.
Definitely. And images, too. Data compression is a huge one. Think about JPEG files for photos or MP3s for music. They use what's called lossy compression.
Meaning some data gets thrown away?
Exactly. The Fourier transform, or a related transform like the DCT for JPEGs, breaks the image or sound down into its frequency components. Then the algorithm decides which frequencies are less important, maybe super high frequencies you can't really see or hear well.
The ingredients you won't miss much if they're reduced.
Precisely. It throws those out, or represents them with less data. That makes the file size way smaller, often without you noticing much difference. It's incredibly efficient.
And it's not just media.
Not at all. Our sources mention its use in finance, believe it or not, for pricing options, and in chemistry, for analyzing the distribution of isotopes. It's this incredibly versatile mathematical tool.
It really is like finding the DNA of a signal, isn't it? You're using it constantly, even if you don't know the name. Okay, so we get the basic idea, and we see it's useful. But things get confusing with all the different names. Fourier series, Fourier transform, DFT, DTFT, FFT. Are they all the same thing?
That's a common point of confusion, for sure. They're all related, part of the same family, but they are distinct tools designed for different types of signals. The main differences boil down to two things. Is the signal continuous in time, like an analog sound wave, or discrete, like digital sample?
Okay, analog versus digital.
And second, is the signal periodic, meaning it repeats perfectly forever, or aperiodic, meaning it doesn't repeat?
Continuous versus discrete, periodic versus aperiodic.
Got it. So let's break them down. First, the Fourier series, FS. This is the original concept, really. It's specifically for signals that are continuous in time, A and D periodic. Think of a perfectly repeating musical note.
Like a sine wave that goes on forever.
Exactly, or even a more complex repeating shape. The Fourier series tells you that any such repeating signal can be built by adding up a set of simple sine and cosine waves, or circles, at specific discrete frequencies, the fundamental frequency, and its harmonics. It gives you a discrete list of ingredients.
Okay, series, continuous, plus periodic input, discrete frequency output.
You got it. Now, the Fourier transform, FT, sometimes called the continuous time Fourier transform, or CTFT to be clear. This generalizes the idea. It's for signals that are continuous in time but aperiodic. They don't repeat.
Like a single clap or someone speaking a sentence.
Perfect examples. Since the signal doesn't repeat, its recipe isn't just a few specific frequencies, but potentially a whole continuous spectrum of frequencies. So the output is a continuous frequency function.
FT and continuous plus a periodic input, continuous frequency output.
Exactly. Now we move to the digital world. Signals are sampled, so they become discrete in time. The discrete time Fourier transform, DTFT, is for signals that are discrete in time and aperiodic. Think of an infinitely long sequence of digital samples.
Discrete time, non-repeating.
Right. Its output, the frequency spectrum, is actually continuous. Interestingly, it's also periodic. The spectrum itself repeats.
Huh, okay. DTFT equals discrete plus a periodic input, continuous but periodic frequency output. Bit weird.
It is a bit weird, but it makes sense mathematically.
Right.
But the DTFT still deals with infinite sequences and continuous outputs, which computers can't handle directly. So that leads us to the workhorse.
The DFT.
The discrete Fourier transform, DFT, this is the practical one for computers. It takes a finite length, discrete time signal as input.
Like a short audio clip or a block of image data.
Exactly. And its output is also a finite length, discrete frequency spectrum. It basically assumes your finite input chunk is one period of an infinitely repeating signal. You can think of the DFT's output as taking specific samples of the DTFT's continuous spectrum.
Okay, DFT will list discrete plus finite input, treated as periodic, discrete plus finite output. That's the one computers calculate.
That's the one. Input and output are both finite lists of numbers. Yeah. Perfect for computation.
Right, but you said DFT. We often hear FFT. What's the F for? Fast.
Exactly. The fast Fourier transform, FFT, isn't actually a different transform. It's just a name for a collection of incredibly clever algorithms or methods for calculating the DFT much, much faster than the straightforward definition would suggest.
Ah, so it's an algorithm, not a transform type. Why was that needed? Was the direct DFT calculation slow?
Slow is an understatement. Calculating the DFT directly from its definition involves a number of operations that grows with the square of the data length. We call that ONNNN. For any reasonably large amount of data, this becomes computationally crippling, just too many calculations.
Okay, give me a sense of scale. How much faster is fast?
It's dramatic. Let's take a signal with, say, 124 data points. Not huge by today's standards. Calculating the DFT directly might have taken something like 25 seconds back when the FT was being developed.
25 seconds for just 1,000 points? Yeah, that's slow if you're doing it constantly.
Right. Now, using an FFT algorithm for the same 124 points, it takes maybe 70 milliseconds?
Milliseconds, wow. That's, what, over 300 times faster?
Easily. And the advantage gets even bigger as the data size increases. Plus, because the FFT involves fewer calculations overall, it often leads to more accurate results. Less chance for small numerical errors to build up.
Yeah.
It was revolutionary.
No kidding. A 300x speedup changes everything. Who came up with this? Was it one person?
The history is actually really interesting and not as simple as one genius inventor. Believe it or not, the core mathematical idea behind the modern FFT was actually figured out, but never published, by the legendary mathematician Carl Friedrich Gauss way back in 1805.
1805, before Fourier himself was even widely known for this stuff.
Yeah, he used it for calculating asteroid orbits, but it kind of got lost or wasn't recognized for its general power. Then, over the years, others developed similar efficient methods for specific problems. People like Frank Gates in statistics in the 30s and Danielson and Lanczos in physics in the 40s.
So the idea kept bubbling up.
It did. But the big moment, the one that really launched the FFT into widespread use, came in 1965 with James Cooley and John Tukey. They independently rediscovered and crucially popularized a general form of the algorithm.
Cooley and Tukey, 1965. What spurred their work?
It's a great story. Tukey apparently got the initial idea while on a presidential advisory committee, thinking about ways to efficiently detect underground nuclear tests using seismograph data.
Whoa, from nuclear test detection.
Yeah. But another person there, Richard Garwin, realized this computational trick could be used for way more than just that. He pushed Cooley, who was at IBM, to program and generalize it. And the rest is history.
That's amazing. No wonder people call it one of the most important algorithms ever.
Absolutely. Gilbert Strain called it the most important numerical algorithm of our lifetime. It made digital signal processing practical on a massive scale. It works using a clever divide-and-conquer strategy, breaking a big DFT down into lots of smaller, easier DFTs.
Okay, so that covers the main Fourier family and the FFT. But our sources also mention related transforms, like Laplace and Z transforms, and something called the convolution theorem. How do they fit in?
Right, good extensions to cover. The Laplace transform, LT, is essentially a generalization of the continuous time Fourier transform. It introduces a complex variable, often called S, which has both a real and an imaginary part.
Unlike the Fourier transform, which just uses the imaginary part for frequency.
Exactly. That extra real part acts like a convergence factor. It allows the Laplace transform to analyze signals that the standard Fourier transform can't handle specifically, signals that might grow infinitely large or are unstable. The FT needs signals to have finite energy.
So Laplace is more powerful for unstable systems?
Precisely. You can think of the Fourier transform as just a special case of the Laplace transform looking only along that imaginary frequency axis.
And the Z transform?
The Z transform, ZT, is basically the discrete time equivalent of the Laplace transform. It does for discrete time signals what Laplace does for continuous time signals. It uses a complex variable Z to handle sequences that might not have finite energy generalizing the DTFT.
Okay, so the place and z are generalizations for handling trickier signals, continuous and discrete, respectively. What about this convolution theorem?
Ah, the convolution theorem. This is a really fundamental and powerful property that connects the time domain and the frequency domain. Convolution is a mathematical operation, kind of like smearing or blending one signal with another. It pops up all the time in systems analysis and signal processing.
And it's usually hard to calculate.
It can be computationally intensive, yes,
Yeah.
but the convolution theorem gives us an incredible shortcut. It states that performing a convolution of two signals in the time domain is equivalent to simply multiplying their individual Fourier transforms in the frequency domain.
Wait, so a complex convolution becomes a simple multiplication.
Exactly. You take the Fourier transform of both signals, which is fast using the FFT, multiply the results together point by point, which is super fast, and then if needed, you can take the inverse Fourier transform, also fast with an inverse FFT, to get the result of the convolution back in the time domain.
That sounds way easier.
It is. It turns a potentially very slow operation into a sequence of much faster ones. This theorem, combined with the FFT, is a cornerstone of efficient digital signal processing. It works the other way. 2 multiplication in time corresponds to convolution in frequency.
Wow. Okay, so we've gone from a smoothie recipe to these incredibly powerful tools like FFT and the convolution theorem that literally shape our digital world. It really is about disassembling signals into their core frequencies and then being able to manipulate or understand them better.
It really is. We've seen the intuition, the applications from earthquakes to JPEGs, the different flavors like series, FT, DFT, the game-changing speed of the FFT thanks to folks like Cooley and Tuckey, building on ideas going back even to Gauss, these broader connections with the place, Z, and convolution.
So as we wrap up, let's go back to that idea of the time spike. That single instantaneous click or flash.
Yeah, that simple event requiring that infinite, perfectly coordinated orchestra of cycles, all aligning at one moment, all canceling at every other moment.
It makes you wonder, doesn't it? What other hidden complex, what underlying harmony might exist in things that seem simple on the surface? Maybe in natural patterns or even, I don't know, patterns in human behavior.
It's a great question. What other intricate recipes are out there waiting to be discovered if we just had the right kind of filters the right way like Fourier's to look at them? Something to think about.